We have been talking about how the projections are made. We looked at the scenarios, how they are created using Earth system models and integrated assessment models with an iteration. The actual projections for, let's say, shown here for RCP 2.6, again remembering that 2.6 corresponds to the radiative imbalance at the top of the atmosphere. Not all models actually get exactly 2.6, but they all follow the protocols of the scenarios prescribed for all the models. That's a common set. And for RCP 8.5, which is pretty close to business as usual, you immediately see that the RCP 8.5 is going to give significantly higher warming and a much more obvious polar amplification that we talked about before. So let's look at what these stippling and these numbers here mean. Okay, so these are changes shown with respect to 1986 to 2005 baseline, so the anomalies with respect to that climatology. Different baselines are used. It's just some compromise. Sometimes 1961 to 1990 is used, but 1986 to 2005 corresponds to a period in which we were already in the very clearly manifest warming from 1980 onwards. Number of CMIP 5 models used to calculate the multi-model mean is indicated in the upper right corner. So you can see 32 for this scenario, 39 here, and in the sea level rise there are only 21 in each of these cases because of the various details that are different for different models participating in the IPCC exercise. Okay, stippling or dots on A and B indicate regions where the projected change is large compared to natural internal variability, and where 90% of the model agree on the sign of the change. So internal variability is just what we talked about. Let's say in the winter you have high seasonal high day-to-day variabilities compared to summer. At high latitudes you have high seasonal variability compared to the tropics, and you have all the other natural modes of variability as well. So everything can be clubbed into internal variability. So the idea is that the trends have to stand out beyond the internal variability, and there is nice work on internal variability by people like Clara Dezer, which show that in regions where internal variability is very high, detecting a trend can be difficult. Okay, that also tells you that the seasonal trends may also be different and more complicated in the winter in high latitudes, for example. Okay, and what else? Hatching diagonal lines shown here in A and B show regions where projected change is less than one standard deviation of the natural internal variability in 20-year means. So that means that the projected change cannot be confidently separated from the natural internal variability. But despite those details, I want to point out something. When you look at the temperature projections, there are mostly regions everywhere where the signal is above the internal variability, and most models agree. Okay, more than 90% of the models agree over most of the regions, except here in this region, which should remind you of your knowledge of the thermohaline circulation, which also occurs here. So this is a region which shows even a negative change compared to the base period of 1986 to 2005, and here it shows a much weaker change compared to the rest of the world. So the heat transport by the thermohaline circulation, and then there are studies showing that there are other factors involved as well, but predominantly, let's say, the Atlantic meridional overturning has an impact here. And the thing to notice is that when you go to precipitation projections, the story is not as coherent. So I think I've already mentioned this a few times. Temperatures tend to have very large, what are called decorrelation scales, which means if I'm sitting here in, let's say, one part of Mumbai, all of Mumbai will have similar temperatures with maybe a slight difference very close to the coast. But it could be raining very differently over different parts. In fact, there are times when extreme rainfall is one order of magnitude different between two spots in the island city of Mumbai. So rainfall in general is like a popcorn, very small decorrelation scales, and models have convective parameterizations and other things which we looked at in terms of uncertainties. And the variability is high, so internal variability is often larger than the projections we're trying to make here. Okay, so this is something to keep in mind. And when you look at change in sea level rise, again, similarly, very fewer models did the scenarios and projections, and you see that for sea level rise, the spatial differences will make a huge contrast. So if you are living somewhere in the island states, global mean sea level rise will not have a meaning for anybody anyways. It's the same for temperature as well, and there are additional complications because if a country like India, which is so close to the ocean, surrounded by ocean on these sides, then increased temperature also comes with increased humidity, and there is something called dew point temperature, which can actually create very dangerous conditions for heat waves. So if the dew point temperature reaches 35 degrees, then the human body is unable to get rid of the heat by sweating, so that can lead to serious issues. So those are the things to keep in mind about projections, other than the fact of all the uncertainties that we talked about. So IPCC has a protocol for reporting uncertainties, and this is part of the protocol of showing stippling and the hatching to show the model differences and comparisons to internal variability and so on. Okay, so there are other details. People like Tim Palmer and Bjorn Stevens write about how these models cannot be trusted with very high confidence at local regional scale, especially when it comes to things like precipitation. And this probably means we should be careful about how we project these uncertainties. So coming back to uncertainty that we looked at already, then sources of uncertainties in projected climate change. We are looking also at the historical model spread here. So models do vary in the historical reconstruction because their own internal El Niños, monsoons, ocean circulation, ocean heat storage, etc. are different, and the details of how the energy is distributed between different components of the Earth system are also slightly different, so they end up with a spread. But the good news is that the spread envelopes the observed trend, which means the models are making a good attempt at staying near to what nature did. So just like we looked at before, internal variability is shown here, which remains fairly steady throughout the 21st century. Model spread increases as you go forward in time, but in the shorter time scales that we talked about before, the model spread is larger than the scenario spread. But as you go out to longer term projections, the model spread increases, but the scenario spread becomes much more dominant. This is what we had mentioned before. Okay. If you look at more specific things like uncertainty in global decadal mean annual temperature versus seasonal temperatures for June, July, August, and December, January, February, and you look at two different places, so you're looking at Europe and East Asia here. So Europe, obviously winter will be more interesting because it's in mid latitudes to higher latitudes where internal variability in the winter is much higher than in the summer. So again, the story is that the model spread is much higher in the beginning, and internal variability is over there, which remains constant, but scenario uncertainty begins to be dominant as you go out. But there is a seasonal dependence on it, and there is a regional dependence as well. So this is the summer temperature for East Asia, and this is the precipitation. Sorry, these are the temperatures and these are the precipitations, and you can see that the sorts of uncertainty are much higher in the models for winter precipitation and summer precipitation, with a bit higher internal variability and model uncertainty. So the main point I want to propose here is that the uncertainties are very region dependent, they are season dependent. Internal variability is also seasonal, because in higher latitudes winters are much more variable, which can make it difficult for models to constrain their uncertainties, as well as well, it's not, you can think of it as signal to noise. So in this case, natural variability acts as a noise, and the signal you are looking for is the change over time. So then the ratio signal to noise can be small. So where internal variability is high, signal can be small and hard to detect, whereas in the tropics you have a flatter seasonal cycle. And other thing that gets complicated in the tropics is that because temperatures are high, small changes can make a big difference in terms of atmospheric response, coupled response, and so on. So keeping all that in mind, the projections are used in various ways with various confidence levels. That depends on the specific applications as well. But we will look at this so-called socially relevant timescale that we mentioned before, decadal timescales. There is also a multi-year timescale attempt now. So we will have to see where the predictability comes from, as I mentioned before. So we'll see that in the next podcast.